Repeat. We have now z equals x plus iy. Then we are going to have the function. Function is nothing but u comma v. U is the function of xy, v is the function of xy. So we are going to have the function. And third one is differentiability. And fourth one is we are going to have del z as del x plus I del y. The first case will be del y equal to 0 and the second case will be del x equal to 0. We are going to have some equations. We are going to equate these two equations. We will get the answer. So this is the idea. Now, so we know that this is a function. We know the complex function is given as w equals f of z. So which is given as u which depends on x comma y plus I v depends on xy. Because x comma y is nothing but x plus I. We know already. And this is for the condition for the differentiability. Differentiation should exist with the limit del z tends to 0. So it exists. And always approaches a unique value as del z or del x and del y, because del z is nothing but del x plus I del y. So 0 in any manner. So z equal to x plus iy. Just now I said del z equals del x plus I del y. So that we can write this equation in terms of x and y in terms of del x and del y. We know already this equation. Okay, just now we have seen this. This is your equation, differential equation. Instead of z, you are going to substitute x plus iy. Instead of del z, you are going to substitute del x plus I del y. That's all. In this equation, we are going to substitute. Okay. So limit del z tends to will go with del x tends to 0, del y tends to 0. What would be our f of z plus del z? This will become x plus del x comma y plus del y. Is it okay? This is okay? Not okay. See, z is nothing but x comma y in a bracket. Del z is nothing but del x comma del y. Here you are going to add plus. So this becomes x plus del x real part. This is your imaginary part. Y plus del y. It means x plus iy plus del x plus I del y. It means, see here, z is nothing but x plus iy plus del z is nothing but del x plus I del y. You are going to add all the four. We have written in terms of notation. This is the notation without I. This is a notation. Is it okay? Very simple. So u can be written as u of x plus del x comma y plus del y. This is your real part. This is your imaginary part. That's all. So similarly, the imaginary part iv x plus del x comma y plus del y minus your f of z will be this one. Your f of z will be, this is your real part and this is your imaginary part. So here it means x plus del x comma y plus del y and imaginary part iv, that also your real part, imaginary part, divided by your del z is nothing but del x plus I del y. The first condition. The first condition we are going to keep del z equal to del x. Del y tends to 0. The first condition. In the second condition, del y tends to 0, del x tends to 0, del y will exist. Okay, so we are going to have two conditions. We are going to take del z to be wholly real, so there will be no imaginary part. Del z equals del x plus I del y. We are going to consider del z as fully real, so there will be no imaginary part. So no imaginary part means del y becomes 0. Your del z equals del x, so del z equal to del x. So your del x plus I del y, this becomes 0. The denominator will be del x alone. Very simple. In the numerator, you have u plus del x, y is there. What of del y? Del y is 0. So comma y. The next term will be iv x plus del x, del y becomes 0, del y is 0, so comma y. And you have the same thing. Any doubt? Now you are going to separate here it contains real part. This is imaginary part. This is real part. This is imaginary part. We are going to separate totally as real part one side, imaginary part on the other side. So you have u is here and u of x comma y is here. So we are going to take the real part. This will be your imaginary part. So taking the real part will give you this term, the first term. Taking the imaginary part will give you second term. I have pulled I out. Other things and all same. So you have limit del x tends to 0. Now take the real part. U which depends on x plus del x comma y. Take the real part from the second term minus u x comma y divided by del x plus, and you know we have taken I common out. So I limit del x tends to 0. Take the imaginary part b x plus del x comma y minus this term minus b of x comma y. What is this one? What is this one? This is differential real part. This is imaginary part. Okay, I agree. But here this is nothing but your differentiable of u. This is your differentiable of v. This is a definition for differentiation. This is what I said earlier. This is a differentiation. See, look at the differentiation. This is in terms of z. This is in terms of u. This is in terms of v. With respect to x here. With respect to x here. This is with respect to z. So this is your partial dz naught by dz usually. So here, so this becomes partial du by dx plus I is here partial dv by dx. So your f dash of z is given by one condition. Very simple one. Now same equation we are going to use now del z equals, yeah, that's all. Del z equals I del y because del x becomes 0. Del z equals I del y. So wherever you find del z, you are going to substitute with I del y. Okay, now of course we know that du by partial du by dx, dv by dx, it's given as they must exist at the point x comma y. Now we are going to consider del z wholly as imaginary one. So earlier we considered as wholly as real part. Now we are going to consider del z wholly as imaginary. So when del x becomes 0, you have del z equals I del y. Substitute. Okay, you will get exactly this equation. See here, instead of del x, you are going to substitute I del y. So del z becomes I del y. Your del x becomes 0. So this becomes 0. This will become 0. Okay, so there will be no del x here. See, in the numerator there is no del x. In the denominator also there is no del x. Only we have only I del y. So as usual, we can separately we can write. This can be written as a real part. This can be written as an imaginary part. So very important thing is you have taken I here and in the denominator one I exists. Don't forget. So now this term will become imaginary part. This term will become a real part. See? Because see here, this I will be cancelled, whereas this I exists. Okay, so this equation becomes 1 by I partial du, differentiability with respect to u. So partial du by dy plus dv by dy. You multiply or divide by I. I have already told you that dividing by imaginary number is meaningless. So we have to always multiply with its complex conjugate. I have already told you. So similarly, 1 by I multiply divide by I. 1 by I means just multiply divide by I. So I divided by I squared is minus 1. So we can write this as minus I. Minus I. I squared becomes minus 1. So that's why minus I. Minus I du by partial du by dy plus partial dv by dy. Now here also we have differentiated. In the first case also we have differentiated. F dash of z. Left hand sides are equal. So right hand side must be equal. Correct? In the first case, see here, this is also your f dash of z. And in the second case, this is also your f dash of z. So we can equate this equation to that equation to get Cauchy Riemann's condition. So we are going to equate these two conditions. So before that, we will have to write as usual du by dy and dv by it should exist at the point x comma y. Okay, so we will have to write all those things. So equation 1 and 2 must be identical. So necessary condition will be you are going to equate these two. When you are going to equate the complex number, you have to equate only with the real part with the real part, imaginary part with the imaginary part, always. So here the real part will be du by dx, here real part will be dv by dy. The imaginary part will be partial dv by dx, which is equal to minus partial du by dy. So which is the necessary condition. This is your Cauchy Riemann conditions. So this is what we use for checking whether the function is analytic or not. We have used these conditions. Any doubt? So these equations are called Cauchy Riemann's differential equations. So partial df by dz exists, it implies that Cauchy Riemann conditions. Okay, it's very important question, and this question will appear in your examination. Okay. Thus the necessary conditions for the function f of z to be analytic at the point z is 4 partial derivatives. We have four partial derivatives. For u there will be 2 derivatives, for v there will be 2 derivatives, one for x, another one for y. So we have du by dx, similarly du by dy, dv by dy, dv by dx, that's all. So 4 partial derivatives satisfy the Cauchy Riemann differential equations at the point z equals x comma y or x plus iy. Now we are going to check. Again, we are going to check whether it is analytic or not. So few problems we are going to deal with. So now we will go for first. We are going for modulus of z. F of z equals. We are going to check modulus of z, whether it is analytic or not. We will find out. So your z equals x plus iy. The modulus of z is nothing but root of x square plus y square. Modulus is nothing but a length from the origin. It's a length from the origin. So you have mod z equals root of x square plus y square. There is no imaginary part here, so v becomes 0. U alone exists. Correct? There is no v here because there is no imaginary part. V equals 0. So u alone exists. Okay. So u plus iv, which is nothing but this is given. Comparing the real and imaginary part. So as I said, v equals 0. Your u is given by this. Now just have dv by dx, dv by dy. Since v equals 0, immediately we can say that surely this will not be analytic. So hence the function is not analytic. Similarly we can say. Okay, because the condition is like this. We have the condition du by dx equal to dv by dy. v becomes 0. So this will not satisfy the condition what it satisfies. So not possible. So hence the function f of z equals mod of z is not analytic function. Now we'll go for the second problem. See, f of z equals real term of z. Real term. RE stands for real term. IM stands for imaginary term. So real of z. What up to real of z? X plus iy. Real of is nothing but x. So u plus iv is nothing but x. U equals 0, v equals 0. So immediately you can say that it is not analytic function. So this will not satisfy because v is not there, doesn't exist. So v is not there. Okay, very simple one. And we are going to have the third problem. Third problem goes like this: f of z equals z. Whether that z itself analytic or not, we will check. F of z equals z. Z is nothing but x plus iy. So you have x plus iy, correct? X plus iy. And x stands for your u and y stands for your v. So we know real part and imaginary part. What about partial du by dx? Answer is 1. Partial dv by dy? Here answer is 1. See, iv is there, correct? You are going to differentiate dv by dy. Your v equals y. v equals y. dv by dy is nothing but 1. So answer is 1. Similarly, du by dy, du by dy, du by dy, answer is 0. dv by dx, answer is 0. So this satisfies. So this is your analytic function because it satisfies one condition. So it satisfies. So f of z equals z is analytic everywhere. We will go for z star. We are going to take the complex conjugate. So x plus iy becomes x minus iy. Where we are going to check whether f of z equals z star is analytic or not. We are going to check. So your x will be your real part and your minus iy will be your real part. Sorry, imaginary part. So this is your real part and this must be your imaginary part. What about the Cauchy Riemann's condition? Partial du by dx, which is equal to 1. What about dv by dy? This is minus 1. But the partial Riemann condition says that du by dx equals dv by dy without minus sign. But here there is a minus sign. It is not analytic. Immediately we can say. See, Cauchy Riemann condition says, this is your Cauchy Riemann condition. du by dx equals dv by dy. Here we have obtained as minus 1. dv by dy is minus 1. This is minus y. Your v equals minus y. dv by dy equals minus 1. Whereas du by dx equals plus 1. So they are not equal. So Cauchy Riemann condition doesn't satisfy. So surely this function is not analytic. Nowhere. Okay. Now we will go for some tedious problem. Okay, so far we have seen only simple examples. So we will go for some bigger problems. F of z equal to z inverse 1 by z. 1 by z is nothing but 1 by x plus iy. I have already told you 1 by xy, it should be multiplied by the complex conjugate. So we have multiplied with the complex conjugate. So in the numerator you have x minus iy. See, denominator will become a real number, x square plus y square. That's the reason that always we have to multiply with its complex conjugate. So x square plus y square. So now this is your f of z. This is your f of z, which is nothing but u plus iv. Now you are going to take separate the real part and imaginary part. Separating the real part, x comma x square plus I square is a real part. Minus I y divided by y square, x square plus y square will be your imaginary part. So this is your u, this is your v. That's all. Now you have to differentiate du by dx, dv by dy and check whether they are equal or not. It should satisfy CR equation. So that's the idea. So your u is given by this and v is given by this. Okay. Of course, one minus sign should exist. Here one minus is there. So there's a mistake here. One minus sign. So minus y divided by x square plus y square. Don't forget. This is minus sign exists. Should exist. Now go and take the partial derivative of u and v. U is given as x divided by x square plus y square. Now you have to use this rule. U by v. That rule. Okay. That rule goes like this. V du minus u dv divided by v square. First I will solve for one term. Rest of the term just you can solve. So now just square the denominator. V square is there. Square the denominator. So this becomes x square plus y square whole square. Keep v as it is. Keep v as it is. So v is nothing but your x square plus y square. You will differentiate du by dx. So differentiating x, that will give you 1. So here 1 multiplied by x square plus y square minus u dv minus what is u? X. So x as it is. So you have to differentiate dv. Okay, you have to differentiate v. So dv by dx. In the denominator you have x square plus y square. Differentiating, that will give you differentiate with respect to x, that will give you 2x plus 0. So 2x. Any doubt? Differentiation according to this rule. So you have now x square plus y square minus 2x square. This can be written as y squared minus x squared. I have pulled one minus sign out. So x squared minus y squared divided by this. Okay. So usually we write x as front. So that's the reason that I have written like this. X and y will never go with y and x. So that's the reason that I have pulled one minus sign out. So now we have found out du by dx, partial du by dx. Similarly, you can calculate partial du by dy using same rule, u by v rule. Then dv by dx, you calculate. So you can also calculate dv by dy and check now CR conditions. Check now du by dx. du by dx equals dv by dy. What of du by dy, which is equal to minus dv by dx. 1 minus this. Look at the Cauchy Riemann conditions. 1 minus sign c, there must be minus sign. 1 minus sign c. This is your Cauchy Riemann conditions. 1 minus sign. Here du by dx, which is equal to dv by dy. dv by dx minus du by dy. Don't forget. Okay. So now this term, these two terms with the minus sign, these two terms are equal. So we can say that the function f of z equal to 1 by z is analytic because it satisfies CR, Cauchy Riemann conditions or equations. Any doubt? Simple one. Now we'll go for the last one. Okay, last session. So this is a Laplace equation. Laplace equation generally is termed as del squared u equals 0, del squared x equal to 0, del squared y equal to 0. Laplace equation. So don't forget, this is general term. Del squared u equals 0. Here u and v are variables. So it must be del squared u equals 0 as well del squared v equal to 0. We are going to have. Generally this is termed as del squared some variable should be equal to 0. This is Laplace equation. Okay. So partial d by dx. Where del stands for d by dx. Actually del stands for I partial d by dx plus j partial d by dy plus k partial d by dz. So this is a term. We are going to square it. When you are going to square it, this becomes Laplace. When you are going to square the del, that will become Laplace. Okay, don't forget. It will be proved later that the derivative of an analytic function f of z itself is analytic. Okay, we are going to prove this later. So by this important fact, we know that u of x comma y and v of x, we know that it's a function. U is a function of x, y. V is also a function of x, y. We'll have continuous and partial derivatives of all orders. In particular, the missed second order derivatives of these functions are given by. Now we are going to have the second order differential equation. So earlier in CR equation only first order differential equation we have used. Now we are going to have second order differential equation. So it means d squared u divided by partial dx dy. D squared u, which is equal to d squared u by partial dy dx. Similarly these two. This is for v and this is for u. If this condition is satisfied, we are going to have Laplace equation. We will see. So we will see now. We know about Cauchy Riemann equation is given by this. We know already. Okay, we know already Cauchy Riemann conditions are given by this equation, and we are going to differentiate now again to go for the second order differential equation. So d squared u by, we are going to differentiate with respect to x. This becomes d squared u by dx squared, left hand side. Any doubt? Come on, listen to me. We are going to differentiate again with respect to x for the second order differential equation. So this left hand side becomes d squared u by dx squared. What about left hand, right hand side? We have to differentiate with respect to x, as I said. So this becomes, numerator becomes d squared v, whereas denominator will be dx dy. Is it okay? Similarly, du by dy, differentiate again. So this becomes d squared u by dy squared. Here it becomes minus d squared v divided by dy dx. Any doubt? Any doubt? So this is for u and this is for v. This is for v. So similarly d squared v divided by dx squared, which is equal to d squared u by dx dy. Similarly d squared v by dy squared, which is equal to d squared u by dx dy. Now we have obtained this one. We will have to equate. So adding equation 1 and 2. So we are going to add equation 1 and 2. We are going to add these two equations. So that will give you d squared u divided by dx squared plus d squared v divided by dx squared. What about right hand side? We will see. D squared u by dx squared plus d squared u by dy squared, which is equal to 0. Similarly del squared v, that also d squared v by dx squared plus d squared v by dy squared, which is equal to 0. See, that's why I said del squared equals 0, it's Laplace one equation with respect to u, and del squared b which is equal to 0 for Laplace equation, another Laplace equation. Okay. So just add these two, will give you this term and this term will go off. You'll have these two terms. You add these two, this term and this term will go off. These two, you will get del squared u. Is it okay? You add this term with this term. You will have d squared u by dx squared plus d squared u by dy squared, which is equal to 0. You add these two terms. See here, they are similar terms. Here also we have similar terms. So this will become 0. You are going to add these two. So you will get this. So this is your Laplace equation. Okay. So thus equations are called Laplace equations in 2 dimensions, whose solutions are the functions of x, which is a function of u, which depends on x comma y, v which depends on x comma y, within the condition that the second order partial derivatives exist. So second order partial derivatives also will exist. We'll try to solve two problems. First one is simple problem, then we'll go for the second problem, which is very tedious. So w equal to f of z equal to z squared. Okay, whether this one satisfies Laplace equation or not, we are going to check. So we know that w equals u plus iv. W equals u plus iv, which is equal to x plus iy whole square. So we know already this. So squaring will give you x squared minus y squared plus i2xy, we know already. So this is your real part and this is your imaginary part. So u is given by this and v is given by this. So this is your u. This is your v. Simple one. Now, what is del squared u? D squared u by dx squared. Okay. Minus d squared u by dy squared. And we know about b. For example, we just take, I have solved only one, we will solve. b equals to 2xy. What is dv by dx? See, b equals 2xy. What is dv by dx? It is 2y. I repeat, b equals 2xy. What is dv by dx? With respect to x, you will have to differentiate. So this becomes 2y. Okay, d squared v by dx squared. There is no x term here. So answer is 0. See, so that's why answer is 0. So d squared v by dx squared equal to 0. Similarly, you will have d squared v by dy squared also will be 0. You just differentiate d squared u by dx squared, for example. This becomes, for example, du by dx. What is the answer? This is your u, correct? U equals x squared minus y squared. What is du by dx? 2x. X squared, when I am going to differentiate x squared minus y squared, we are going to differentiate, this becomes 2x. D squared u by dx squared is 2. What is du by dy? Minus 2y. Don't forget. What is d squared u by dy squared? Minus 2. So answer will be 2 minus 2, which is equal to 0. So it satisfies Laplace equation, del squared equal to 0, del squared v equal to 0. So this function is nothing but Laplace function. It satisfies the Laplace equation. Any doubt? So very important sum. This problem often will appear in the examination. So this is the last problem that we are going to see. Prove that u equals x squared minus y squared. And v is given as y divided by x plus y squared. They are harmonic function of x and y. We are going to check whether it is harmonic function. Sometimes we call this as harmonic function. Laplace equation sometimes we call this harmonic functions. Harmonic functions of x and y, but are not harmonic conjugate. Okay, we are going to see in detail. So given as u equals x squared minus y squared, v is y by x squared plus y squared. So it is given. They are harmonic functions. They must satisfy Laplace equation. So u is given as this. What is du by dx? 2x. Simple one. What is d squared u by dx squared? 2. Very simple. Okay, so we'll stop